What is up, guys? We are chugging along, picking up with chapter 14, acid-base equilibria. So we are also doing chapter 15, sections 2 and 3. So in our last module 2 weeks ago, we did chapters 13 and then 15.1. So now we are picking up with 14 and 15.2, 15.3. Starting off with chapter 14. We are going to be going through Bronsted-Lowry acids and bases, pH and POH, relative strengths of acids and bases, hydrolysis of salts, polyprotic acids, buffers, and acid-base titrations. So our starting picture shows us the sinkhole, and these happen between reactions between acidic groundwaters and basic rock formations like limestone. Acid rain can also lead to these forming because then you get that acid-base reaction in the soil, and then eventually you get these sinkholes that can form due to that erosion of the soil and rock. So we're going to start it off with 14.1, Bronsted-Lowry acids and bases. So here we're going to identify acids, bases, and conjugate acid-base pairs according to the Bronsted-Lowry definition. Write equations for acid and base ionization reactions. Use the ion product constant for water to calculate hydronium and hydroxide ion concentrations. And describe the acid-base behavior of amphiprotic substances. So let's start off with the definition brought to us by Johannes Bronsted and Thomas Lowry in 1923. So these guys looked at reactions taking place between acids and bases. And they define the Bronsted-Lowry acid as a compound that donates a proton to another compound. And a Bronsted-Lowry base is a compound that accepts a proton. So when we're saying a proton, we're actually talking about H+. So when you think about the hydrogen atom, you have one proton and one electron. But if it doesn't have that electron, it's just a proton. So when we're talking about donating a proton, again, we're talking about H+. So an acid gives H+ to another, and a base accepts H+. So types of compounds that can be acids, they can be both an organic, which is carbon-based, or inorganic compound. You can have cations that contain hydrogen, and you can even have anions that contain hydrogen. These can all be acids. Bases tend to be maybe an ionic compound that contains NaOH, something like sodium hydroxide, NaOH. They can be molecules. These tend to be amines, and amines are nitrogen containing. So something like NH3 or NHCH3, these are all amines. They can be anions, either with a hydrogen or without one, and they can also be cations, but there's really not that many examples. So the species that is formed when a proton is removed from an acid is called the acid's conjugate base. So for instance, HCl is an acid. Its conjugate base now takes this proton off, so its conjugate base is Cl-. So Cl-, the chloride ion, can accept a proton, making it a base. And then the species formed when a proton is added to a base is the conjugate acid. So the conjugate acid of Cl- is HCl. So these are called a conjugate pair. If you have a species that can accept or donate a proton, it is called amphiprotic. So water is a big example of this. It can serve as an acid or a base, and we're going to look a lot more into water as we go along in this chapter. If you have it in the presence of an acid, it acts as a base and accepts a proton. If it's in the presence of a base, it acts like an acid and donates a proton. And here's an example. So when you have an acid-base reaction, you have two conjugate pairs. So you have an acid and a base on each side of your reaction arrow. So that means that if one thing is your acid, the other thing has to be your base. You can't have two acids doing an acid-base reaction. So, for instance, here we have water and ammonia in equilibrium with hydroxide and ammonium ions. So water here is acting as the acid. It's giving one of its protons, so sometimes it's easier to write it as HOH. It's giving one of its protons to the ammonia, so that means it's acting as an acid. So now its conjugate base that it forms is OH minus. And ammonia is accepting a proton, so that makes it a base, and its conjugate acid then is NH4 plus. So that means that in the reverse reaction, NH4 plus acts as an acid and gives an H, or proton, to OH minus, which is the base. So the reaction between a Bronsted-Lowry acid and water is called acid ionization, because that's what you're doing. When you take something, maybe something like hydrogen fluoride, and react it with water, you make some ions. You get H3O plus and F minus. So we get this fluoride ion and hydronium ions. One thing to just note is a lot of times chemists, we are lazy. We like to shorten everything we possibly can. So a lot of times you might see H3O plus written as H plus. They're the same thing. Not so much in reactions, but when we're doing some calculations, that can happen. So again, here's that reaction and showing it both in a skeletal form and then their formulas. Similarly, if you have a Bronsted-Lowry base reacting with water, we have base ionization. Here's an example. Water is reacting with this base here. This is pyridine. Don't worry about the name and the structure. This is an organic compound, but you can see they have a nitrogen here. This is an amine also. So water here is acting as an acid, giving a proton to the nitrogen in pyridine, then forming this conjugate acid to pyridine, which has this H here, and we have an overall positive charge, and OH minus. So we again are forming those two ions. Now water is pretty cool because in pure water, so all you have is liquid water, water acts as both an acid and a base. So one water molecule might act as an acid while the other is acting as a base. So we have H2O plus H2O, equilibrium with H3O plus and OH minus. And we could say the Kw, okay, so good old reaction equilibrium constant, is equal to the concentration of H3O plus times OH minus. We don't include the two waters in that because they are liquid. Remember, liquids and solids do not go in equilibrium equations. And this Kw at 25 degrees Celsius is equal to 1 times 10 to the negative 14th power. So basically what's happening here, if I were to just kind of draw this out a little more, is one water is giving its hydrogen to another. So one is acting as an acid, the other is acting as a base to then form H3O and OH minus. Here it is, drawn a lot better than I can do. But again, you can see, whoops, your acid here is giving this hydrogen to the oxygen in water to form H3O plus and OH minus. So water does react with itself in autoionization. And yes, Kw does depend on temperature. Generally, though, we focus on the Kw at 25 degrees C of 1 times 10 to the negative 14th power. So let's go ahead and look at an example. We want to know the hydronium ion concentration and the hydroxide ion concentration in pure water at 25 degrees Celsius. So we know that this is pure water, this is autoionization, so the concentration of hydronium and hydroxide are equal. Okay, and we'll say that this is equal to, each one of those is equal then to X. So Kw is equal to H3O plus times OH minus. And yes, those concentrations of hydronium and hydroxide can change, but when we are talking about pure water, that means there's nothing in there to change one of those two concentrations. So they are equal to each other if you have pure water. So Kw is equal to H3O plus times OH minus. So this is 1.00 times 10 to the negative 14th power is equal to X times X squared. So we take the square root of both sides, and we get that X is equal to 1.0 times 10 to the negative 7th molar. And this is a very important concentration to keep in the back of your head, write it down somewhere, because how the concentration of either one changes is going to decide if our solution is acidic or basic. And we'll talk more about that in the next section. So let's look at another example. We're told a solution of acid in water has a hydronium ion concentration of 2.0 times 10 to the negative 6 molar. What is the concentration of hydroxide ion at 25 degrees Celsius? So we know at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14th power. And we know that that is equal also to the concentration of H3O plus times OH minus. And then we know hydronium, we know H3O, but we don't know OH minus. So to get hydroxide, we need to take Kw and divide it by H3O. So that now is equal to 1.0 times 10 to the negative 14th divided by H3O, which we're told is 2.0 times 10 to the negative 6th. And this gives us 5.0 times 10 to the negative 9th molar. So one thing to notice here is we're told this is an acid in water. So since this is an acid, the concentration of hydronium is going to be higher than hydroxide because you have more ions to give these H pluses or over to water to make H3O. So you're going to make more H3O than OH minus. You can go back and check your work. If you take this OH concentration, multiply it times your hydronium concentration, you should get Kw 1.0 times 10 to the negative 14th. So when you're thinking about this, think Le Chatelier's principle. We're increasing one of our reactants by adding more acid, so we're going to shift our reaction. All right. So let's look at another example, looking at acid-base behavior of an amphoteric substance. So we're going to look at the equations for the reaction of let me rewrite this, HSO3 minus, like that, with A as an acid with hydroxide and B as a base with HI. So we're told it's amphoteric. And so if it's acting as an acid, that means it's going to be giving away its proton. So we have HSO3 minus plus OH minus. So since we are giving away, that we have only one hydrogen here to give away. So that means our conjugate base of HSO3 minus is going to be SO3 2 minus now, because now we've lost another positive charge. And that is now plus H2O. So what you should notice here also is we are still charge balanced. We have a total of -2 on the left side of the reaction. On the right side, we still have a total of -2. So these can also consider these redox reactions. Fun fact. I don't know if it's fun or not. Okay, and now in the next part, we want it to act as a base. So that means it's going to accept a proton. Okay, so since it's accepting, that means this H from HI is going to go over to it. So now we're going to have H2SO3. Now, since we just added this plus charge to a negative, now we have a total of 0. So now this is just H2SO3 plus, now the conjugate base of HI is going to be I minus.